Okay, let's continue the discussion about section 4.4. Okay, so we have already discussed the Cauchy theorem. The Cauchy theorem says if you have an analytic function over the simply connected region and arbitrary loop closed contour, and the integral is always 0. This comes from the deformation invariance theorem. The deformation invariance theorem says if you have two curves, gamma 0 and gamma 1, one is deformable to the other one. Then the integral, and f is analytic, of course, so we always talk about analytic function. Then this the integral does not change. Okay. Okay. Last time we did one computation, and now let's continue the discussion of an example. The example is the following. So we have evaluate the integral e to z over z squared minus 9 dz. Okay. So here we see that this function, if we call it f of z is e to z over z squared minus 9. This function is analytic except only z equal to plus or minus 3. Z squared minus 9 equal to 0, then z equal to plus minus 3. So it's analytic except those 2 points. So where is a plus minus 3? Here's a plus minus 3, plus 3, and minus 3. The circle is a circle with radius 2. So this circle does not include any of the 3 or negative 3 inside. So here we can apply the Cauchy theorem. The Cauchy theorem says if the function is analytic over the inside, then inside of the loop, then the integral is 0. The integral is 0. Okay. Or you can consider that this circle is deformable to a point. And then the integral of f over the point is 0, and plus the deformation invariance theorem, you still get 0. So anyway, we have 0 here. Okay, so if your circle, if your the loop does not surround any of a bad point, then the integral is always 0. And here, when we say they equal to each other and they don't equal to 0, we only assume f is analytic in this analysis part. If f is also analytic in this big disk, then both of 0. Both of integral are 0, so there's nothing to discuss. It's just by the Cauchy integral theorem. Okay. Okay, and then next example. So let's talk about the function 1 over z minus a, and the loop gamma is any circle not passing through a and traversed once in the counterclockwise orientation. Okay, counterclockwise. So you have a point A. Possibly your circle is like this. We never say that A is the center, so it may not be the center. Counterclockwise. It's always counterclockwise. Or gamma is here. Counterclockwise. Okay, so if this A is inside gamma, it's like this case, case 1. If it is inside of the gamma, so we can technically shrink this circle to a circle centered at A with a radius, whatever radius r. The new circle is also traversed counterclockwise once. So just use deformation to shrink this bigger circle gamma to the small circle centered at the point A with radius r, whatever radius, small enough. And there is a circle, let's call it little gamma, centered at A with radius r, traversed once in the counterclockwise orientation. Okay? Counterclockwise like this. And we see that gamma and little gamma are continuously deformable to each other. And we know that the integral of f over little gamma, whenever it's centered at A with radius r, we did a lot of computation. It's always 2 pi I, counterclockwise orientation. And by the deformation invariance theorem, then the integral of f z dz along capital gamma is equal to the integral of f z dz over little gamma is equal to 2 pi I. Okay. So when it's inside the gamma, it's equal to 2 pi I. It doesn't matter where you place this capital gamma. In case 2, A is not inside gamma. A is not inside gamma, then gamma is continuously deformable to a point, a constant curve. If it is continuously deformable to a point, then the integral of f of z dz along capital gamma is always 0. Okay, so inside 2 pi I, outside 0. So we get those are two results. We get these two results. And one of the important factor is that this orientation should be always counterclockwise and traversed once. Okay, if you get multiple round, then you will have multiple copies of 2 pi. If you change the orientation, you will get a negative 2 pi. Okay. Next example. We're going to evaluate 3z minus 2 over z squared minus 2 along gamma. Here, what is this gamma? The gamma is a following thing. So this is 0, this is 1. Okay? Oh, this is z squared minus z. First of all, we have to see which point is a bad point for the definition, which point is not inside definition of the function. So f of z is a 3z minus 2 over z squared minus z is undefined at z equal to 0 or z equal to 1. Because at 0 and at 1, z squared minus z is equal to 0. The denominator cannot be 0, so it's undefined at 0 and 1. Okay, so we have these 2 points, these 2 special points labeled. And for this curve, we can shrink it a little bit. So we are going to shrink this curve so that it looks like this. This curve is counterclockwise orientation. Okay, so what is the new curve? This is a gamma. The new curve is like this. So you start from this point, you go counterclockwise orientation, and then move to the right circle. And right circle is also counterclockwise orientation, and follow the same segment back to this, back to the left circle. Okay, and this we call it the left circle is C1, right circle is C2. And remember the interval, the whole thing is called the gamma. So gamma, capital gamma is continuously deformable to little gamma. The little gamma is C0 union C1 union from left to right. Let's put this as 1/3, 2/3. 1/3, 2/3, and a union 2/3, 1/3. We are talking about the segment, the oriented segment, not just the interval. Okay, so first of all, function is analytic over this domain between little gamma and capital gamma. It's not analytic over those 2 points, but you already use 2 disks to cover this 2 points. So outside this, the f is analytic. So the integral of f gamma is equal to integral of f little gamma. And the little gamma, this place, you go from left to right once, right to left once. So they are cancelled. So you only have 2 parts, 2 circles, counterclockwise oriented circles. Okay, so if you want, you can write this way. we put 1/3, 2/3, we put 2/3, 1/3, and these two are cancelled, okay, because they have the different orientation. Okay, then for each of them, here, this circle only contains 0, it does not contain 1. And here it only contains 1, it does not contain 0. And back to this function, 3z minus 2 over z squared minus z. We can use partial fraction to write it in the difference. So the partial fraction is the following. It is equal to 2 over z plus 1 over z minus 1. 1 over z minus 1. How do we do that? We set it equal to a over z plus b over z minus 1. Remember that we did this in the partial fraction method in the differentiation in calculus. And then you do the multiplication. Az minus 1 plus bz is zz minus 1, and you use a system equation to determine a and b. So a is 2, b is 1. And let's check. So the integral is equal to the integral z over 2 plus z minus 1 over 2 over z plus 1 over z minus 1 over c0 dz plus the integral over c1 2 over z plus 1 over z minus 1 dz. Okay, remember c0 contains 0, c1 contains 1. c0 contains 0, but it does not contain 1, so this is an analytic function. It's analytic. Analytic function inside the c0. So the integral along c0 is going to be 0. Here, it contains 1, does not contain 0, so this one is analytic. Inside c1, this is inside c0. So those two terms, they disappear after integration. So you only have 2 over z c0 dz plus 1 over z minus 1 dz c1. Okay? So this number 2 can be moved forward. You get 1 over z. 1 over z, you can write it like z minus 0 c0 dz. Here is just 1 over z dz. Right? And this one, remember, it contains the point 0 is inside c0. So the integral is 2 pi times 2 is 4 pi I. Here you see 1. Here the 1 is inside the z1, so the integral is 2 pi I. They're both counterclockwise. So the total answer is 6 pi I. 6 pi. Okay? So we get the answer equal to 6 pi, even we don't really do the integral. Right? The other example. So we're going to integrate 1 over z squared minus 1 dz along the gamma, where gamma is like this. This is a 1, this is a negative 1. It looks a very strange curve. Okay, this is gamma. Gamma includes negative 1, but exclude 1. 1 is here. Let's put 1. 1 is equal to here. And it's a counterclockwise orientation. Okay, so first of all, we are going to just draw a small disk, gamma. And gamma is continuously deformable to little gamma. Okay, so continuously deformable to little gamma. And then the integral 1 over z squared minus 1 dz over gamma can be written as a integral 1 over z squared minus z dz over little gamma. Okay, now let's continue the discussion. Of course, you can pick up the special angle, special radius. For example, gamma is centered at the -1 with radius little r, and you solve it. Or you can use partial fraction. Again, here we use a partial fraction. The partial fraction, if you do it, it is a 1 over 2 times z minus 1 minus 2 times z plus 1. Okay, so that's the partial fraction. Technically, you get 1/2 and -1/2 for a and b, but whatever, you know how to do it. And this integral becomes an integral. Let's move 1/2 forward. Z minus 1 dz minus 1/2 integral z plus 1 dz over gamma and over gamma. This function is analytic inside the circle, inside the gamma. This is analytic. It's not analytic only at 1, but 1 is far from this point. So it's analytic inside the gamma. The integral is 0 minus. Here, it's not analytic. It's a 1 over z minus -1. So it's 1 over z minus a, that a is inside the gamma, so it's a 2 pi I. And the counterclockwise orientation, 2 pi I. So -1/2 times 2 pi I is -pi I. Okay, so what did we do for those computation? We first find the bad point. The point function has 0 denominator, and then we use small circle to label the those bad point, and we shrink the large curve to these small circles. And each small circle, if it traverses counterclockwise or counterclockwise once, then it's equal to 2 pi I. If it traverses more than one time, it will be integer multiples of 2 pi I. Okay, so that's the rest of the examples in this section, continuous deformation. Okay, so that's a section of 4.4. That's the end of section 4.4. And now let's see the section 4.5, the integral formula, the Cauchy integral formula. And its consequences. Okay, so the Cauchy integral formula is the following theorem. Theorem says let gamma be a simply closed positively oriented contour. Okay. Closed. It must be closed. If f is analytic, in some simply connected domain D containing gamma, and z0 is any point inside gamma, then f of z0 is equal to 1 over 2 pi I integral fz z minus z0 dz along gamma. Okay, so the analytic function can be written as an integral with this special form of a function. First of all, this function is not an analytic function over the interior part of gamma, because z cannot be z0. We already said that z0 is any point inside the disk, so this function is not analytic inside. Okay, then you do the integral. It is equal to f of z0. Okay, if this part you put any analytic function, any function analytic over the interior part, then this integral becomes 0. Okay. It's not the counterexample for the integral theory. Integral theorem. Integral theorem requires analyticity of the whole interior part. Okay, now let's prove it. Let's prove why this is true. Let's prove why it is true. Okay, so this function f of z over z minus z0, it's analytic except z equal to z0. It's analytic except z equal to z0. Let me draw it here also. Then what we can do, we can find a small enough r such that the whole closed disk centered at z0 with radius r is totally inside the interior part of gamma. It's inside gamma, so we get this. Okay, this is our set. We call it CR. The corresponding circle is denoted by CR with a counterclockwise orientation. With counterclockwise orientation. Okay. Then you see here the function fz over z minus z0 is analytic between gamma and CR. So over this analysis, this function is analytic. So by deformation, invariance theorem, then we have the integral of fz over z minus z0 dz along gamma is equal to the integral of z minus z0 over CR. Okay. Okay, so that's the first step. We don't want a irregular gamma, so we want a regular gamma. Okay, once we have the regular gamma, let's check. We're going to evaluate this integral of z over z minus z0 CR dz. We do the addition and subtraction trick. We do addition and subtraction trick for the numerator. Okay, and fz0 is a constant. You move it forward, then you get 1 over z minus z0. z0 is inside the gamma, and that gives you 2 pi I. 2 pi I times fz0. Okay, let me copy it here. So in order to prove the theorem, we need to show that this part will disappear, will be 0. Okay, and the process is the following. We know that this small enough r, so once r is small enough, any smaller r will also satisfy the whole process. So we are going to compute the limit r approaching 0 into the left hand side is constant. Left hand side is equal to this integral over gamma. Right hand side, this is constant. Only this term may or may not change. We don't know, but it may change, whatever. So we're going to compute, if after limit this is 0, then we finish the proof. Okay? So we want to check if this is 0 or not. Okay, so let's compute let's estimate. So we have fz minus fz0 over z minus z0. Let's put fz minus fz0. fz0 is fixed number. z is over the circle. So f is analytic function. So f is continuous, and then continuous function over the circle is always bounded. Let's assume the upper bound is m. The upper bound, of course, depends on r, and the denominator is just r. Denominator is distance between z and z0. Z is from the circle, so the distance is equal to r. Okay, then when we compute the limit at dz, it is less than or equal to the integral cr fz minus fz0 absolute value over r dz. Okay, and this one, it is less than or equal to mr over r. Integral of dz over cr is 2 pi r, is a circumference, and 2 pi r to r cancelled is a 2 pi mr. What is mr? Mr is a supremum. Z belongs to cr absolute value of fz minus fz0. Yeah. Okay, so this is mr. The maximum value over the circle is a continuous function. The maximum value is a finite number, and also f is continuous. F analytic f is of course continuous. F is continuous, then the difference will approach 0 because it continues. It approaches fz0. Fz approaches fz0, then absolute value of fz minus fz0 is going to be 0. So this term approaches 0, and times 2 pi still approaches 0. Yes. The integral fz minus fz0, z minus z0 dz is equal to 0. And this is 0, this term is 0, so you get the original, so you get the statement. So integral fz z minus z0 over gamma dz is equal to 2 pi I times fz0. 2 pi minus fz0. Okay, and that's it. That's it. You divide by 2 pi, you get the statement. Okay. So the analytic function is an integral, and integral is the evaluation of analytic function at the bottom point. So let's see the example. Assume we have this integral where this gamma is a circle centered at 2 with radius 3. Gamma is a circle centered at 2 with radius 3. 1, 2, 3. Centered at 2 with radius 3, so it's a negative one. It's very big. Okay. And this function, you see here, it's a z minus 0. It's z minus 0. 0 is here. 0 is inside. So here, this one will be our f. F of z over z minus 0. The integral over the gamma. So here fz is e to z plus sine z, and z0 is 0. Okay, fz, this is a numerator, and z0 is a z minus 0. It's 0. So that's by the integral by the Cauchy formula. This integral is equal to 2 pi I times a function evaluated at 0. Okay, 2 pi, remember integral formula has a coefficient 2 pi. If you put it with the integral, it's a 1 over 2 pi. If you put it with the function, it's a 2 pi times the function evaluated at 0. Here is a function. So e to 0 is a 1, sine 0 is 0. So this is a 1. That's just 2 pi. Okay? That's the computation based on the Cauchy integral formula. Okay. Okay, the second example, the function is cosine z over z squared minus 4. The integral, the closed contour is this gamma. We will not give the concrete description. It's just sketched in the z plane. This closed contour only contain 2. It does not contain negative 2. So in order to apply the Cauchy integral formula, we need to factor z squared minus 4 as a z minus 2, z plus 2, and we have to combine the plus 2 together with the cosine, because only 2 is included in the closed contour. This part is okay. Okay, so what is a function? So here, f of z is cosine of z plus 2. This function is analytic of the whole interior part of gamma. And z0 is equal to 2. So the integral fz over z minus z0 along gamma dz, it is equal to 2 pi I f of z0. Okay, so it's a 2 pi I times cosine of 2 over 4. So it's like this. Okay. So we only leave z minus z0 in the numerator if z0 is inside the closed contour. If it's not inside the closed contour, you can lift it to the f part. Okay, so next we want to connect the integral formula with the derivative. Check here, we have f of z is equal to integral gamma f cosine minus z and d cosine. We just change the symbol, change the notation. We can use z instead of z0, and then this looks like a function. F z0 looks like the evaluation. That's only difference. The same thing. Okay, if you have a function, you can do the differentiation. We expect f prime of z. You see here, we only differentiated z, so we will understand this as first we do the differentiation d dz, and differentiation integration can commute. This Leibniz formula. And this you just apply the chain rule. It's a chain rule. F cosine does not depend on z. Z minus cosine minus z. This z is a variable. So you apply the chain rule, you will have this formula. So that's what we expect. So we're going to prove what we expect. Let G be a continuous function on the contour gamma, and for each z not on gamma, define capital G of z to be the integral of g of cosine minus z along gamma d cosine. Okay. Then G is analytic at each point not on gamma, and its derivative is given by g prime of z is equal to the integral g of psi minus z squared dz, d psi, sorry, d psi along gamma. Okay, so that's exactly what we expect. We just want to prove what we expect. Okay. So here there are two things we want to point out. First, gamma is a contour mean. May not closed. Okay. Gamma is not necessarily a closed set. And second, little g is only continuous. It's not required to be analytic. Okay. And three, capital G of z and little g of z have no relation. Why? Capital G of z, capital G is defined for z not on gamma. Little g is defined for z on gamma. So they are not have the same value. Even the limit. Because gamma is just a curve, so maybe you have a sequence approach to the point. Then this is gamma g, and this is a little capital G. This is little g. Even with the limit value, we don't have the equality. But with this definition, we can say that the capital G of z is differentiable. So that's the stuff. Okay, so we are going to show the derivative of g is little g. The derivative of capital G is little g. So what is the derivative? The derivative this is derivative. Then derivative is defined by the integral. Okay, sorry, not derivative. Each term is defined by the integral. So you just plug in the definition and do the necessary computation. This is equal to the integral along gamma g of psi d psi minus z minus delta z and psi minus z. Okay. Okay. So this is the ratio, and then we want to prove the limit of this is equal to this formula. So we get the difference, and what is this? You do this one minus this one, and after the subtraction, I skip some middle step. It is equal to this. Okay, just use this term to subtract this term, and it will be like this. You simplify it and find the common denominator and simplify the numerator. So you factor out 1 delta z. 1 delta z does not depend on the point psi on the gamma. Okay, so we're going to let we will let delta z approach 0. We will show that this is 0. Okay? Okay, let's see why. You have a curve, gamma compact. It's an image of 0, 1. It's compact. Gamma is continuous, so image is compact. And you have the point z. Z has distance between z and the gamma, so this is the distance we call d. And delta z should be very small. Remember, delta z will approach 0, so we assume this delta z is d is the distance between z and gamma, and delta z is less than 1/2 of d, so we want them small enough. And g is continuous on gamma. Gamma is compact, so there is an capital M greater than 0 such that upper value of g of z is less than or equal to m. It has upper bound. Okay, then let's check. We are going to estimate here the g of cosine over cosine minus z minus delta and times z minus cosine minus z squared. Okay, you see cosine is here, delta z is here, so delta z plus delta z is more or less this place. So the distance this distance is greater than 1/2 d. This distance is greater than 1/2 d. And cosine minus z, the distance is greater than d, greater than or equal to d. So they're both in the denominator, so it's less than or equal to less than or equal to what? Less than or equal to g of cosine is less than or equal to m. And this is less than or equal to d over 2. This is less than or equal to d squared, so it's 2m over d cubed. Okay, and then what we have? We have this part. The whole thing, I'll put up its value. G z plus delta z minus g of z over delta z minus integral g of cosine d cosine minus z gamma is less than or equal to upper value of delta z integral over gamma g of cosine minus z minus delta z and cosine minus z squared d cosine. Okay, this one is less than d over 2, and this one is less than, as you see here, it's a 2m d cubed. And then you integrate the upper value of d cosine along gamma. It's L of gamma. L of gamma. And dd cancelled, 2 cancelled, so you will get the m length of gamma over d squared. We possibly have to leave this delta z. No, sorry, this part. We have to leave this delta z. Yeah, it's my bad. I couldn't cancel it. If I cancel it, nothing will approach 0, so this is cubed. So 2 delta z. This one is fixed. Well, z is fixed, d is fixed, z is fixed, this d is fixed, so this is a fixed number. That's my bad. This is a fixed number, then this approaches 0 as delta z approaches 0. Delta z will become smaller and smaller. the previous part we only have upper bound, it's useless. Okay, so this implies the g prime is equal to g of psi d psi minus z squared along gamma, and the g is of course analytic. Okay, so we'll stop here today, and we will continue next time to the consequence of this theorem. Okay.